Alright, another video on the Professor Lewin Controversy. Sort of an interesting subject, so it's probably worth talking about some more, and there's some more information now. We get a diagram of what he was modeling, something that was published in the Journal of Physics in 1982, of the basic experiment. And what I do now understand, listening carefully, is that this coil is not AC. I mean, it's not a changing magnetic field. He's just measuring the voltage on initialization. So it's not really a moving coil. It's not a moving magnetic field. It's just an increasing one from turning it on, and then it's over. The experiment's over in a millisecond or whatever. So that's why they have to use oscilloscopes, obviously. So I say it flaws this whole thing a little bit, but for my purposes it'll be fine. So the battery would essentially be the original Lewin drawing. It would be in the bottom of those two resistors. There'd be a battery there, you know, well, on one side or the other, you know, and then you'd end up with the reasonable of voltage at the 2 points, and it would be 0.9 volts because of the resistors consuming the extra 0.1 volt because they're essentially in series in the other experiment. But anyway, sort of. Anyway, so I'll redraw it and just do it the way it needs. I think it should be understood is what's so it's a huge change in a circuit. And then the idea of the 2 voltmeters on either side. So my first argument, you just look at the diagram and you say, okay, let's just take the whole middle thing out, the hexagon in the middle. And then what do you have? You have 2 voltmeters and a loop. And it's so you have the same thing. So I guess what I wanted to get to, sort of, was they don't really give you any idea, any conceptualization. What the hell happened there? Wrong button. That button is the one I wanted. You know, a lot of these rules they have about you want to find out what's happening in a circuit. You know, then you. So let me just draw this part of it, and just so we understand the shape they're using. Essentially, so the idea is that you know, they decide how much current or energy is going to be captured by a loop by always doing this idea of a Gaussian surface and all this other crap, where you contrive a surface and then take its area. And what they're really doing when they're doing that is they're really just saying, let's take an area and then make it into a circle, and then take the average of that circle and we'll call that a radius. So they're just really taking this shape and changing it, you know, by area, just taking its area of this weird shape and saying, okay, let's convert that into a circle, and then we can have an average that will be the radius. So you can see the distances are different, and so there's an average for this shape of wire in terms of a radius, and that'll define essentially the circumference of the wire, and that's really the only thing that matters in this experiment. I mean, sort of the radius matters because of the R rule, where the magnetic field diminishes with distance at R squared, I think, for a dipole anyway, and R for a monopole. I think that's the way it works. But anyway, so I'm being tentative because, you know, that could be incorrect, but I'm just saying the idea should be understandable. So I would argue, so I could redraw this as just a magnetic field, and then you have a loop of wire, so we'll make it round just to take away all this nonsense in here. And the thing that's just being ignored is what's causing the current in the wire. And the idea is there's a bunch of these vectors, these lines of force coming off of the inductor, okay, especially as it's increasing. So the lines start off being kind of far apart, and then as the magnets moved or turned on, the idea would be as those lines get tighter and tighter, or more numerous, you could argue. So, and it's only in a circumstance where those lines are changing that you can induce a current. So, you know, that's sort of the rule. So you could sort of think of it as you're taking this pressure that's evenly distributed across the whole surface, and trying to figure out in some way it's supposed to be making a current in a wire. Okay, but the catch to this is always the way you measure those currents. If I took a wire loop like this and just put a loop of wire, nobody would sit there and say, I can just put a voltmeter on here, you know, and measure voltage. I mean, no one would have the expectation that that's going to work. You know, the idea would be they'd have to break the loop. The loop would have to have be you know, horseshoe shaped, you know, something, so you could have a plus side and a minus side, and then you have the coil inside. Yeah, probably should use the other pen for that part. So the idea would be is the loop would have to have a break in it, and then you could measure the voltage across the break. You know, there would be a plus side, and then there'd be a minus side, and you could measure the voltage. So the idea is there's supposed to be 1 volt in this thing based on this circumference, the size of this loop compared to the strength of the magnetic field being created. But obviously it doesn't have its full strength until it has a peak. You know, it's moving, so the idea is it's coming out of, okay, it's coming towards you. It's coming towards the loop, and so like I said, the field is going to get stronger and stronger as it gets closer and closer, and there's going to be a peak amount of current, and then there'll be nothing. And to me, the real question is the voltage is the real thing to be trying to figure out. So the first argument that I've made is that if you extend these little lines, they're obviously going to hit the wire of the voltmeter. So the voltmeter is creating its own loop. Okay, that is filling. Okay, it's getting affected by the magnet, the changing field, however you want to describe it. So the changing field is hitting the wire of the voltmeter, which is problem A. Okay, that's one problem you have in trying to measure. The second problem in trying to measure is you really don't have a place in this circuit. It's not really a circuit. It's creating pressure in all these locations. Now, the idea is that there's this right-hand rule, you know, where everything, you know, where the current, if it's coming towards you, that the current is somehow going counterclockwise, which in my opinion means the voltage is going clockwise. Okay, so current and voltage, because they say they go opposite directions. So you could argue, or I would argue, so let's put a semi-block in the wire, and those would be the resistors. So we take our loop now that you can't measure anything because it's just a circle. It doesn't have a it doesn't have a plus or minus side, so it's getting pressurized evenly all the way around. So how could you measure a voltage? But now we put a resistor in there, and the one of them's a larger, you know, 9 times bigger than the other one. So one's 1 worth. So one's an easy path and one's a hard path. I guess I could argue that if we obey these loop rules, that we say there's a tendency for a current to go a certain direction in a wire for whatever reason. Okay, like water spiraling in a toilet, it has a direction, it just does that. And you could argue that the wire, so these are semi-breaks in the wire, so just understand these as like breaking the wire, in a sense, the resistors. It's a little bit like breaking the wire, kind of. And I would argue that this whole wire, like any charge phenomenon, this whole piece here kind of wants to go one side positive, one side negative. And we could argue that the loop rule is that it, not the loop rule, the right hand rule is basically an illustration of the fact that the voltage goes one way, because one side has to go positive and one side goes negative. So I would argue that this side goes positive, so this side charges the full, well, whatever it is. See, they're using it's 1 volt is in the system, and that's how much voltage you're creating in this wire, is 1 volt. And so the idea is that we have 0.9 and should have 0.9 and then 0.1, and that would equal 1. But anyway, so this side goes positive, this side goes negative. Illustrate better here, maybe. I don't know how to exactly make it clear. So this wire, essentially, the positive charges, it's probably more exactly the neutral, the unpressurized stuff. It doesn't really matter. So this has low pressure, this has high pressure, and the opposite thing's going to happen at this end. So this end's going to be the negative end, or the 0. So and this would have the 1 volt potential over here. So this would be the positive. So this would on this resistor you have a plus 1 volt of pressure at one end, and you have 0 at the other end across this resistor, which is the big resistor. So if you were to measure the voltage across this resistor, you would have, because it's hard to get through, you would have 0.9 volt reading, because the voltage isn't going to escape easy. So you're going to build up pressure at this end, because it won't be able to just go through the resistor. On this other side, you're going to have what appears to be, obviously now you have a switch in polarity, because if you hook the voltmeter up the same way, it's going to give you an opposite reading, because now you have your 1 volt here and you have 0 here, and now you have an easy path, which means that most of the voltage leaks out, so you only have 0.1, and it'll be negative. So that's how I would interpret it, as what's actually happening. So Professor Lewin, in a sense, is right, in the sense that you should get 0.1 and 9 measuring across these resistors. If you follow this idea that these wires are essentially charging, and that they're in a sense independent because of the resistance, and so you're essentially measuring, if you could, the voltage across these two wires. But again, the problem is how do you measure them without this problem, without the influence of the field on the voltmeters? All right, so what else to say about this? Yeah, so I guess it just comes down to whether in this circumstance you can assume that the pressure does migrate, creates a dipole in the wire, forces the wire to polarize, like certain things are forced to polarize. Like two plates can be moved into each other, and one of them goes positive and one of them goes negative. Even though they had no charge, one of them is obliged to go one way and one is obliged to go the other way. And the tendency is in this creating current in wire thing, is that the wire tends to push the voltage like I said, I don't know why they're following currents, because it just doesn't seem like the right way to do it. But anyway, so what else can be said about this? But the idea of measuring 2 points and getting 2 different readings can only really happen, 2 points up here. Like I said, if he hooked the meter right to the resistors, I guess is my point. My point is this hunk of wire from here to here, okay, this piece in here, and this piece in here. They're the things that are essentially becoming batteries, right? So it's like you're putting 2 batteries in the circuit now, and you're just switching their polarity, because one is going right to left, one's going left to right. And so it's like, so you're just basically redoing the experiment with, yeah, I guess that's the way I wanted to say it. So you're just basically redoing the experiment with, let's see, draw this correctly. All right, so here's the 2 resistors, and we'll just draw it in color, and then you can see the difference, hopefully. I already did it wrong, so if I turn it upside down, that might still work out. Yeah, okay. It might work out, except for the paper's the wrong size now. But anyway, and so, yeah, no, it's still wrong. All right, so yeah, turning it over didn't work. All right, I'm just going to make this red, and well, you'll just have to imagine I didn't make that mistake. And this one would be the red side here. Well, the red side is actually the positive side, which is the negative side, which is not the right, because of the whole way they got everything wrong. But this is how you could look at it. Oh, did the wrong color again. Jesus. It's rough here. There's a lot of rough stuff going on. So I would argue that this is essentially what you're turning the circuit into, is 2 batteries now, because the wires are the inductors. The resistors are probably doing some inducting, but most resistors, you can get resistors that are actually a coil of wire, a lot of little wire, just to create the resistance of the wire, and they make resistors that way. But most of them are composites. And so how much they induce current, that is, how much you can induce a current in one of these carbon resistors, they might not, if you made a whole loop out of resistor material, you might not even be able to conduct you might not even be able to induce a voltage into it very well. This is not a very good conductor, and it certainly doesn't have to be made out of much metal. So the resistors, like I said, are sort of dead spots, openings, gaps, and you can measure across those gaps, and yeah. So that's sort of how I would diagram it, is yeah, so you're just really measuring 2 different batteries affecting a across a resistor, if you can measure it, depending on, but I mean, you definitely have to be on one side or the other side, or your probe wires are what's really creating the effect. So again, the argument is, where do you connect your probe wire? Because you can't connect it in between this gap, and this artificial battery doesn't have a plus and a minus side on it explicitly. So you can't just probe here and say that is this whole wire. You can't just probe here and say that's this whole wire. And that's part of the problem with trying to figure this out. So anyway, I don't think I need to say much more, but that's how I would look at it. So they don't really account for the fact that this magnetic field is pressurizing the wire. And it's just about, where can the pressure go? And why does it go there? And yeah, so I think that's enough of an explanation from how I would look at it. So I'm saying that in a sense, Professor Lewin, in saying that Faraday's right, if he's saying, okay, well, all Faraday's is no, it still doesn't work by Faraday. You know, it's just, this is different than the standard system. It's just not a plus and minus system. So you can't just sit there and say, I put an inductor in it and I automatically properly created voltages. Because again, the only way they measure them traditionally is to put the loop in the wire, and the wire will automatically, but the wire will create a positive and a negative side. But where it does that, okay, how it does that is not the part being explained. And the same problem exists in here, is how do you find the positive and the negative voltage? And is there really that created? Because you could legitimately say that, let's say it doesn't, and this whole wire just charges to 1 volt at all locations. I mean, theoretically it could read 1 volt everywhere, and this could be 1 volt everywhere. Theoretically. Well, anyway, so Hoffaday did do a video on the subject, but I don't think he provided any insight at all, and he said a couple of things that are fairly annoying, you know, regarding his expectations again for alternative theories. He's pretty much convinced the universe isn't a real thing somehow, and that you know, there's material doesn't mean anything. You know, there's no materiality technically, and I don't see how technically it could make a difference whether it's material or not. It's obviously a real system doing real things, in the sense that they're happening right in front of us. So to try to say, well, it doesn't matter what your theory is because it's nothing, so you'll never be able to prove the universe is something, so don't bother. If you can't look at it with a photon, you can't say it exists. I mean, that kind of nonsense. It just, so yes, he is probably a waste of time. I would remove him from the top of my list. Yeah, because he is brain dead. Anyway, till next time, and such, I think. Yeah. So I guess I've made my point. The point is that if this was your voltmeter and you put it around this whole thing, you'd recognize that it would read a voltage if you put it around this whole experiment. It would read the voltage. So you can't probe this experiment without being part of the experiment. Yeah. Simple enough. Till next time.